What if the most powerful machine humanity has ever switched on works so well that we cannot explain it without arguing about how many universes there are? That is not a thought experiment. In a cold laboratory in California, Google's Willow chip did in minutes what the cosmos does not contain enough time to do, and its own creator suggested the calculation was borrowed from parallel worlds we can never see. Maybe he was right. Maybe he made a beautiful mistake. Tonight, we are going to find out which. So pour something warm, find your softest blanket, and let me take you to the edge of what a machine can show us about reality, and the place where reality quietly refuses to answer. Part 1. 5 minutes against the age of the universe. On the 9th of December, 2024, in a quiet laboratory in Santa Barbara, California, a small object, roughly the size of a coin, finished a calculation. It sat at the center of a tangle of gold wiring and copper plates, sealed inside a chamber colder than the empty space between the stars. The whole apparatus had been engineered to do one thing, which was to keep this little chip undisturbed long enough to think. And on that morning, it thought for less than 5 minutes, produced its answer, and went quiet again. Nothing about the moment looked dramatic. There was no flash, no sound, no tremor in the floor. And yet the people standing around that machine understood that they had just watched something happen that, by every reasonable accounting, should not have been able to happen at all. The calculation that little chip performed was one that the fastest supercomputer on Earth could not finish. I do not mean that it would have taken the supercomputer a long time. I mean that it would have taken it a length of time so enormous that the words we normally use for a long time stop having any meaning. The estimate that Google's researchers published was 10 septillion years. Let me say that number more slowly, because it is the kind of number your mind will try to round off and discard, and I want you to actually hold it for a moment. 10 septillion is a 1 followed by 25 zeros. 10,000 trillion years. To feel how strange that is, you need something to compare it against, because a number that size means nothing on its own. So, here is the comparison. Our universe, as far as we can measure, is about 13.8 billion years old. That is the entire span from the beginning of everything, from the first expansion of space itself, all the way to this present moment, with you sitting, wherever you are sitting, listening to my voice. 13.8 billion years. And 10 septillion years is roughly a quadrillion times longer than that. So if you took the whole history of the cosmos, every star that has ever burned, every galaxy that has ever turned, and you ran that entire history over again from the beginning, and then again and again, 1,000,000 billion times in a row, you would still not have waited long enough for the supercomputer to finish the job that the little chip finished over a coffee break. I want to dwell on the strangeness of that machine for a moment longer, because the physical reality of it makes the numbers feel even less believable. That chip was not running in some exotic facility on another world. It was sitting in a metal canister, cooled to a fraction of a degree above absolute zero, which is colder than the deepest reaches of empty space between the galaxies. The reason for the cold is simple, and tells you how fragile the whole thing is. The slightest warmth, the faintest vibration, a single particle of light wandering in from the wrong direction would have been enough to ruin the calculation entirely. So this object that supposedly outran the lifetime of the cosmos, a quadrillion times over, could be destroyed by a whisper of heat. It is, at once, the most powerful calculator humanity has ever switched on and one of the most delicate objects we have ever built. And both of those things are true in the same 5 minutes. The task it performed, the one that would take the supercomputer 10 septillion years, was a peculiar one, and I will explain it properly later, but for now just hold the shape of it. The machine was asked to do something that produces a pattern of results so tangled so woven through with quantum interference that no ordinary step-by-step computer could reproduce the pattern without, in effect, simulating the entire quantum dance from the inside. And that simulation is what would take the impossible stretch of time. The chip did not simulate the dance. The chip simply performed it because it is itself a quantum thing. And that is the seed of the whole mystery. A classical computer would need the universe's worth of time to fake what the quantum chip did naturally, in minutes, just by being what it is. This is the part where you would expect the scientists who built the machine to step forward and say something proud and ordinary. You would expect them to say, "Look how clever our engineering is, look how far the technology has come." And they did say some of that. But the founder of the team that built it, a man named Hartmut Neven, said something else as well, something that did not sound like an engineer at all. He looked at that result, the calculation that outran the lifespan of the universe many times over, and he wrote that it lent credence to the idea that the computation had happened in many parallel universes at once. He wrote that it supported the notion that we live in a multiverse. Now, sit with how unusual that is. This was not a mystic. This was not a man selling a book about crystals and cosmic consciousness. This was the head of one of the most serious quantum computing programs on the planet, writing in an official announcement, saying in effect that his machine had been so fast it must have borrowed the work from other versions of reality. He was suggesting that the chip did not do all of its thinking here, in the world you and I share, but reached sideways into worlds we cannot see and quietly recruited them to help. And that is the question I want to walk through with you tonight, slowly, patiently, with no rush at all. Because underneath the headlines, underneath the words parallel universe, that lit up across the internet for a few weeks and then faded, there is a real question, and it is one of the strangest questions a human being can ask. When a machine does something that the entire universe does not contain enough time to do, where, exactly, did the work get done? Where did the computation actually happen? Not in a poetic sense, in a physical sense. Where were the numbers crunched? I want to be honest with you about what kind of journey this is going to be, because there are two cheap ways to tell this story, and I am not interested in either of them. One cheap way is to tell you that yes, the multiverse is real. Science has proven it. There are infinite copies of you living infinite lives. And isn't that wonderful and terrifying? The other cheap way is to roll my eyes and tell you it is all hype, that a corporate scientist got carried away, and that there is nothing here but a fast piece of metal. Both of those stories are easy, and both of them are wrong, or at least both of them skip over the actual truth, which is far more interesting than either. The truth is that this little chip has reopened an argument that physics has been quietly avoiding for almost exactly 100 years. It is an argument about what is really there when no one is looking. It is an argument that Einstein and Bohr had in the 1920s and never resolved, and the chip did not settle that argument. What the chip did was something subtler and, I think, more haunting. It took a question that used to live only in philosophy seminars and thought experiments, and it built a machine that makes that question impossible to keep ignoring. So, this is not really a story about computers. I want you to let go of the idea that you are about to learn about gadgets. This is a story about reality, and about the possibility that the reality you experience, the single solid world of one outcome following another, is a kind of surface. A thin, calm surface stretched over something much larger, something the universe seems to keep carefully out of our sight. The title of this video says these machines found something we were never meant to see. By the end of our time together, you will understand exactly what that phrase means and why it might be more literal than it sounds. We have about 2 hours. There is no hurry. Get comfortable, settle in, and let me start where the strangeness starts, which is not with universes at all, but with a single, almost impossibly small thing and a small lie that almost everyone has been told about it. Because before we can ask where the computation happened, we have to be honest about what a quantum computer actually is, and the honest answer is stranger than the comforting one you have probably heard. Is less than break time equals 1s is greater than number. Part 2. What a qubit really is, and the lie we tell about it. Let me begin with something familiar, because the strangeness lands harder when you start from solid ground. Every computer you have ever used, the phone in your hand, the laptop on the table, the servers humming somewhere far away that hold your photographs, all of them are built out of one tiny, humble idea. The idea is the bit. A bit is a switch. It can be on or it can be off. We write those two states as 1 and 0, and that is genuinely all there is at the bottom. Everything you have ever seen on a screen, every song, every face, every word, is built out of billions upon billions of these switches, each one sitting in one of two positions, on or off, 1 or 0. The whole digital world is a cathedral built from that single brick. A quantum computer is built from a different kind of brick, and that brick is called a qubit. And here is where you have to let your intuition loosen its grip a little, because a qubit does not behave like a switch. A qubit, before you look at it, is not simply on or off. It exists in what physicists call a superposition, which means it holds a combination of both possibilities at the same time, weighted, blended together in a way that has no equivalent in the ordinary world. It is not secretly one or the other while you are not looking. As far as the mathematics and the experiments can tell us, it is genuinely both, held in a delicate balance until the moment something measures it and forces it to choose. Now, one qubit holding two possibilities is interesting but not yet astonishing. The astonishing part is what happens when you put qubits together. With two qubits, you do not get two possibilities. You get 4, all held at once. The combinations of off-off, off-on, on-off, and on-on all present together. With 3 qubits, you get 8. With 4, 16. And you can already feel the shape of this, the way it climbs. Every single qubit you add does not increase the count by a little, it doubles it. 10 qubits hold more than 1,000 combinations at once. 20 qubits hold more than 1,000,000, and the climb does not slow down. It accelerates, faster and faster, into territory that very quickly stops making sense. The chip in Santa Barbara, the one called Willow, has 105 qubits. So let me tell you what 105 qubits means, and I want to warn you in advance that the number is going to sound made up. 105 qubits, in superposition, represent roughly 4, followed by 31 zeros of combinations, all tracked at the same time, 4 times 10 to the 31st power. To put that in something, you can almost touch, that is more than the number of grains of sand on every beach and in every desert on Earth, multiplied by itself. And here is the part that should genuinely stop you. If you could build a quantum computer with just 300 good qubits, not 300,000, not 3 million, just 300, it would track more separate numbers at the same time than there are atoms in the entire observable universe. A chip you could hold between 2 fingers, keeping account of more values at once than there are particles in everything we can see through every telescope ever built. And this is exactly the moment where the famous, comforting explanation shows up, and I have to gently take it away from you because it is not quite true, and the way it is not true matters enormously for everything that follows. The explanation you have heard is that a quantum computer is fast because it tries every possible answer at once. It holds all those combinations in superposition, the story goes, so it just checks all of them simultaneously, and that is why it can do in 5 minutes what would take a normal computer the age of the universe. It is a lovely image. It is also wrong, and if you believe it, you will misunderstand the rest of this story. Here is why it is wrong. Yes, the qubits can hold all those combinations at once, but you cannot read them all out. The instant you measure a quantum computer, that whole shimmering superposition collapses, and you get exactly one answer, chosen at random according to certain probabilities. If all the machine did was hold every possibility and then let you look, you would simply pull out one random combination, like reaching into a bag of billions of lottery tickets and grabbing one without looking. That is useless. A bag of random answers helps no one. So the parallel universe-sounding magic of trying everything at once, taken on its own, gives you nothing at all. The real trick, the thing that makes a quantum computer powerful, is far more elegant and far stranger than brute force parallel guessing. The trick is called interference. To understand it, picture the surface of a pond and imagine dropping two stones into it at the same time. Ripples spread out from each splash, and where two ripples meet, something specific happens. If a crest meets a crest, they add together and you get a taller wave. If a crest meets a trough, they cancel and the water goes flat as if no ripple had ever been there. This adding and cancelling is called interference, and it is one of the most basic behaviors of any wave. The combinations inside a quantum computer behave like waves. Each possible answer carries something like a ripple, and a quantum algorithm is, at its core, a carefully designed piece of choreography. The whole art of it is to arrange the calculation so that the ripples belonging to all the wrong answers meet crest to trough and cancel each other out, flattening into nothing, while the ripples belonging to the right answer meet crest to crest and reinforce, growing tall and strong. So when you finally measure, the wrong answers have erased themselves, and the answer you are overwhelmingly likely to pull out is the correct one. The machine is not trying everything and reading the pile. It is conducting an orchestra of possibilities so that the wrong notes silence themselves and only the right note rings out. There is a second ingredient that makes this possible, and it is called entanglement. When qubits become entangled, they stop being separate individuals. They link together so completely that the state of the whole group holds information that simply is not present in any single qubit on its own. You can know everything there is to know about each piece and still not know the secret that lives only in the connection between them. This is not a theory anyone is guessing at, by the way. Entanglement has been confirmed in laboratories thousands of times, so convincingly that the 2022 Nobel Prize in Physics was given to 3 scientists who nailed it down beyond any reasonable doubt. The world really does work this way. We are not speculating about whether these strange behaviors are real. We are only arguing about what they mean. It is worth lingering on just how counterintuitive that interference really is, because it is the thing that separates a quantum computer from a merely very large, ordinary one. In an everyday computer, possibilities do not cancel each other. If you list 1,000,000 guesses, all 1,000,000 of them just sit there, and you have to check each one. But in a quantum computer, the possibilities are more like overlapping sounds than like items on a list, and sounds can silence each other. Play 2 tones that are perfectly out of step, and instead of hearing them twice as loud, you hear nothing, because the peaks of one fill the valleys of the other. Noise-cancelling headphones work on exactly this principle, generating a sound wave shaped to flatten the roar of an engine into silence. A quantum algorithm is doing something disturbingly similar with answers. It generates the quantum equivalent of an anti-sound, precisely shaped so that every wrong answer is cancelled into silence, leaving only the one tone you were trying to hear. The wrong answers do not get checked and rejected. They erase themselves before you ever look. And that is genuinely difficult to picture happening inside a small chip, which is part of why the question of location nags at us so much. When 1,000,000 wrong answers cancel one another, where did that cancelling take place? It is not like erasing pencil marks one at a time. It is as though all the answers existed together, vividly enough to interfere, and then most of them annihilated each other in a single coordinated stroke. For that to happen, in some sense, all those answers had to be somewhere, doing something at the same moment. Hold on to that unease. It is the same unease David Deutsch turned into the most famous argument in this entire field. And now we arrive back at our question, and you can feel that it has grown teeth. Those combinations, the 4 followed by 31 zeros of them, are real enough to do work. They interfere with each other. They cancel and reinforce. They carry out a calculation that no ordinary machine could match. And yet the physical chip is just 100-odd little circuits of superconducting metal, chilled near absolute zero. So where, exactly, are all those numbers being kept while the machine does its thinking? Where does the bookkeeping live? When the wrong answers cancel and the right answer survives, what is the stage on which that drama is being acted out, if the stage clearly cannot fit inside one small piece of cold metal? Now, a careful person, a skeptic, will already be raising a hand at this point, and I want you to hold their objection in mind, because we will come back to it and take it seriously. The skeptic says, those numbers do not live in any real place at all. They live in mathematics. They are entries in an abstract equation, and you are making a childish mistake if you go looking for a physical warehouse to store them in. Maybe the skeptic is right. We will test that idea carefully later. But for now, just notice that the question refuses to go away easily, and that even phrasing it forces you to take a position on what is real. Because here is the thing. One man asked exactly this question, in exactly this way, almost 40 years ago, long before any machine like Willow existed. He looked at what a quantum computer would have to do, purely on paper, and he came to a conclusion so strong and so strange that most of his colleagues simply did not want to follow him there. He said the answer to where does the computation happen was obvious, and that the only reason people would not accept it was that they could not stomach what it implied. And tonight, decades later, a machine in California produced the exact kind of number he said would one day force everyone to confront his question. So, let me introduce you to him, because you cannot understand what Hartmut Neven meant without first understanding the quiet, stubborn man whose 40-year-old argument he was leaning on. Is less than break time equals 1s is greater than number. Part 3. The man who said it 40 years ago. The man's name is David Deutsch, and if the field of quantum computing has a founding prophet, it is him. He is a physicist at Oxford, and he is, by every account, an unusual person, even by the standards of theoretical physicists, which is saying something. He is famously reclusive. For long stretches of his life, he has rarely left his house, working from home, sleeping at odd hours, conducting much of his thinking and his correspondence in solitude. He is not a builder of machines. He has spent his career thinking about what is possible in principle, about the deepest rules that govern what can and cannot be computed, and about what those rules tell us about the structure of reality itself. And in 1985, he wrote a paper that quietly laid the foundation for the entire field that would later produce the chip in Santa Barbara. In that paper, Deutsch did something nobody had quite done before. He worked out, in rigorous mathematical detail, what a universal quantum computer would be. He described a machine that used the strange rules of quantum mechanics, the superposition, and the interference we just talked about to compute. Decades before anyone could build such a thing, he laid down its theory. And in the middle of that work, almost as an aside, but with complete seriousness, he wrote a sentence that has been echoing through the foundations of physics ever since. He wrote that the behavior of quantum computation places, in his words, an intolerable strain on all interpretations of quantum theory other than Everett's. To understand that sentence, you need to know what Everett's interpretation is, so let me explain it as simply and as honestly as I can. In 1957, a young physicist named Hugh Everett proposed a radical answer to the question of what happens during a quantum measurement. The orthodox view said that when you measure a quantum system, the superposition collapses and reality picks one outcome. Everett said, "What if it never collapses? What if, instead, every possible outcome actually happens, and reality itself splits, branching into separate versions, one for each possible result? In one branch, the particle went left. In another branch, equally real, the particle went right. And crucially, you split too. There is a version of you who saw it go left and a version of you who saw it go right, and both are completely real and neither has any way of reaching the other. This is the many worlds interpretation. It says the universe is not a single unfolding history, but a constantly branching tree of histories, all of them real, all of them happening. There is a sad and human story behind that idea, and it is worth a moment because it shows you how unwelcome this picture of reality was when it first arrived. Hugh Everett proposed his theory as a young graduate student at Princeton, and the reception was so cold that it effectively ended his career in physics before it began. The towering figures of the field treated the idea as an embarrassment, something not to be taken seriously, and Everett, discouraged, left academic physics almost entirely. He went to work for the defense establishment, doing mathematical analysis of weapons and strategy, and he never held a physics post. The man who may have written down the true structure of reality spent his working life as a contractor and died relatively young, largely unrecognized for the thing that would later bear his name. It was only decades after his proposal that physicists, Deutsch prominent among them, began to argue that the young man had been right all along and that his colleagues had recoiled not because the idea was wrong, but because it was unbearable. Now, most physicists, when they first hear this, recoil. It sounds absurd. It sounds like uncountable copies of everything, endlessly multiplying, a new layer of reality born every time a particle wobbles. And for a long time the many worlds idea sat at the fringe, respected by a few, dismissed by many as philosophical excess. But David Deutsch did not dismiss it. Deutsch took the mathematics of quantum mechanics absolutely literally, more literally than almost anyone, and he argued that many worlds was not the strange option. He argued it was the obvious one, the only one that did not require you to bolt extra, unexplained rules onto a theory that worked perfectly well without them. And his single sharpest argument for this, the one I want to give you carefully because it is the spine of everything Neven was reaching toward, comes from quantum computation itself. Here is the argument, and I am going to build it slowly. Imagine a quantum computer running a famous procedure called Shor's algorithm, which is a method for taking a very large number and finding the smaller numbers that multiply together to make it. This is a genuinely hard problem for ordinary computers, so hard that the security of much of the internet depends on it being hard. Now imagine you set a quantum computer to factor a truly enormous number, the kind that would matter for breaking real codes. Deutsch sat down and asked a simple question. While the machine is doing this, how many computational steps, how many individual operations are actually being performed to get the answer? And the number he arrived at was staggering. For a sufficiently large number, the calculation effectively uses something on the order of 10 to the 500th power of computational resources. 10 followed by 500 zeros. Now hold that against reality. We talked earlier about the atoms in the observable universe, all the particles in everything we can see. That number is about 10 to the 80th power, 10 followed by 80 zeros. And 10 to the 500th is not a little bigger than 10 to the 80th. It is unfathomably, catastrophically bigger. The gap between them is itself a number with hundreds of zeros. There are not remotely enough atoms in the entire visible universe to write down, to track, or to physically embody that many computational steps. Not even close. Not if you used every single particle in every galaxy as a tiny abacus bead. So Deutsch asked the question that I have been circling with you this whole time, but now with the full weight behind it. When the quantum computer factors that number, where did all those computations happen? They happened somewhere. The answer came out. The work got done. But the work required more resources than the entire visible universe contains. In Deutsch's own words, if the visible universe were the whole of physical reality, then physical reality would not even remotely contain the resources required to perform the calculation. The conclusion he draws is direct and unflinching. The resources are real, they must exist somewhere, and since they cannot fit in the universe we see, they must exist in the universes we cannot see. The computation, he says, is spread across the branches. The other worlds are not a metaphor. They are where the extra work is being done. Let me give you a picture for this, because the abstract numbers can numb you. Imagine you walk past a tiny workshop, just a small shed really, with one workbench inside. And in a single afternoon, that little shed produces more finished automobiles than could be built by every factory on the entire planet, running continuously since the universe began. You would not stand there and say, "What remarkable productivity." You would say, "That is impossible. There is not enough room in that shed. There are not enough hands. Something I cannot see is helping. Where are the extra workers?" That is precisely Deutsch's question about the quantum computer, and his answer is that the extra workers are real, and they are standing in rooms next to ours that we have no door to open. I want to be completely honest with you about the status of this argument, because honesty is the only thing that makes a story like this worth your time. What Deutsch offers is an argument, not a measurement. It is an interpretation of why the machine works, a way of making sense of the impossible-seeming resources. He has not photographed another universe. He has not received a signal from one. He has built a chain of reasoning that he finds overwhelming and that many other brilliant people find unconvincing. It is one of the most powerful arguments for the multiverse anyone has ever made, and it is also, as we will see, an argument with a clear escape hatch that his critics are happy to use. But for 40 years, it was mostly abstract, a debate about machines that did not yet exist, fought with chalk on blackboards. And that is what changed in December of 2024. For the first time, a real device, sitting on a real bench, produced a real number so far beyond the universe's capacity to keep up that people could feel the force of Deutsch's old question in their stomachs, rather than just on paper. 10 septillion years. The resources the machine seemed to draw on simply did not fit. And so, when Hartmut Neven wrote his announcement, he did not invent a wild new claim out of nowhere. He pointed straight back at David Deutsch. He named him. He said this result lends credence to the multiverse prediction first made by Deutsch. The prophet had spent 40 years insisting the math demanded other worlds, and now the head of a major laboratory was standing in front of a working machine and saying, perhaps he was right all along. But the moment those words were published, something happened that tells you more about the true state of reality than the chip itself ever could. Half of the physics world stood up to object, not politely, sharply. They said Neven had made a basic error, that he had confused a piece of mathematics for a place, that the machine proved nothing of the kind. And the argument that broke out, the collision between the people who saw other universes in that chip and the people who saw only clever metal and abstract equations, is where the real story lives. So let me take you into that fight, because to judge who is right, you first have to understand the thing they are actually fighting about. And it is not the data. It is a hole in the theory that has been sitting there, unfilled, since the 1920s, is less than break time, equals 1s, is greater than number, part 4. Hartmut Neven lights the fuse. Let me set the scene properly, because the way this announcement was made matters almost as much as what it said. In December of 2024, Google published two things at once. There was a formal scientific paper in the journal Nature, the kind of careful, peer-reviewed document where every claim is hedged and measured. And there was a company blog post, written for the public, meant to explain to ordinary people why this chip mattered. The blog post is where the famous sentence lived. Describing the 10 septillion year result, the team wrote that this number exceeds known timescales in physics, and that it lends credence to the notion that quantum computation occurs in many parallel universes, in line with the idea that we live in a multiverse, a prediction first made by David Deutsch. I want you to notice something about that wording, because it is more careful than the headlines that followed made it sound. Neven did not write that Google had proven the multiverse. He did not write that they had opened a door to another world and looked through it. He used the phrase, lends credence. It is a soft phrase, a careful phrase. It means something like, this makes the idea a little more plausible, but the internet does not run on careful phrases. Within days, the headlines had hardened the soft claim into something solid and electric. Google says its quantum chip proves parallel universes exist. Google appears to have accessed other dimensions. The careful hedge evaporated, and what was left was pure wonder and pure exaggeration, racing around the world. It is worth pausing on how a soft scientific phrase mutates as it travels, because the same thing happens to almost every story like this one, and learning to see it is a kind of intellectual self-defense. A researcher writes lends credence, which is a careful way of saying this nudges the odds slightly. A science outlet reports that the chip indicates parallel universes, dropping the hedge. A larger outlet reports that Google says parallel universes exist, dropping the uncertainty entirely. And by the time the story reaches a casual reader scrolling at the end of a long day, it has become Google has accessed other dimensions, a flat statement of accomplished fact about something that was never claimed. Nothing was lied about at any single step. Each version was only a little bolder than the last. But the distance between the first sentence and the last is the distance between honest science and science fiction, and it was travelled in about 72 hours. To understand why even the soft version of the claim was so startling, you need to know that Google actually announced two completely different achievements that day, and the world paid attention to the wrong one. The first achievement was the one the researchers themselves were most proud of, and it is genuinely, soberly, enormously important. It is also, unfortunately, very difficult to fit into an exciting headline. It is called below threshold error correction. Here is what that means, and why it is such a big deal. Quantum computers are fragile almost beyond belief. The delicate superpositions we talked about, the shimmering combinations that do all the work, fall apart at the slightest disturbance. A stray vibration, a flicker of heat, a single photon of light wandering in from the wrong direction, and the whole quantum state collapses into useless noise. For decades, this created a brutal problem. To protect the information, you needed to spread it across many physical qubits, so that if one failed, the others preserved the answer. But here was the cruel catch. Every qubit you added to help with error correction was itself another fragile thing that could fail. So for a long time, adding more qubits made the situation worse, not better. The errors piled up faster than you could correct them. It was like trying to plug leaks in a boat with planks that each had their own new leaks. What Willow demonstrated, for the first time convincingly, was a way out of that trap. The researchers built encoded qubits out of grids of physical qubits. First a small grid, then a larger one, then a larger one still. And as the grids got bigger, the error rate went down. Each time they scaled up, the encoded qubit got more reliable, not less. They had crossed a threshold, a tipping point, beyond which adding more qubits actually helps. This is the result that working quantum scientists celebrated, because it is the thing that makes large, useful quantum computers possible in principle. It is the difference between a dream and a roadmap, and almost nobody outside the field paid it any attention at all, because it does not sound like a doorway to another universe. It sounds like an engineering footnote. But it was the real treasure in that announcement. Let me make sure you feel why, because it is the difference between a dream and a plan. For years, the great fear hanging over the entire field was that quantum computers might be fundamentally impossible to scale up, that the fragility would always win, that every time you tried to build something bigger, you would simply add more places for errors to creep in, until the whole machine drowned in its own noise. If that fear had been correct, then quantum computing would forever remain a laboratory curiosity, a handful of qubits doing toy problems, never growing into anything that could break codes or design medicines or do any of the things people dream about. What Willow's error correction showed is that the fear was not correct. There is a path. Cross the threshold, and bigger becomes better instead of worse. It is the moment a fragile experiment became, at least in principle, a buildable technology. And the bitter irony is that this genuinely historic result, the one that working physicists will still be talking about in 50 years, was almost entirely drowned out by a single sentence about parallel universes that the same scientists tucked into a blog post. The quiet truth was the revolution. The loud claim was the headline. There is one more thing about Neven's framing worth holding up to the light, because it reveals how naturally even careful scientists slip into the language of other worlds. When Neven said the computation may have happened across parallel universes, he was not being sloppy or sensational by the standards of his own field. He was using a way of speaking that has been common among quantum computing researchers for decades, precisely because it is such an intuitive way to describe what the machine seems to do. It is far easier to say the calculation was shared across many worlds than to say the calculation explored a high-dimensional region of an abstract mathematical state space. The multiverse language is vivid, it is graspable, it makes the impossible speed feel almost reasonable, and that very convenience is part of the danger, because a way of speaking can quietly harden into a belief about what is real until people forget they were ever using a metaphor at all. The second achievement was the loud one, the random circuit sampling result, the 10 septillion years. And I have to tell you something about that task that will matter a great deal later, so plant it in your mind now. Random circuit sampling is, by design, a useless calculation. I mean that almost literally. It does not solve any practical problem. It does not factor a number, or design a drug, or break a code. It was chosen precisely because it is extremely hard for a classical computer to fake and easy for a quantum computer to do, which makes it a perfect benchmark, a perfect way to show off raw quantum power. But the answer it produces is, in practical terms, worthless. It is a demonstration, a flexing of muscle, not a useful act. Keep that in your back pocket. It becomes important when we ask, later, whether the machine really did anything that needed other universes, or just something showy. So here is the emotional core of this part, the thing I find genuinely remarkable and want you to feel. The man who built the machine looked at his own creation, at a result he and his team had engineered with their own hands, and he could not fully explain it within the boundaries of a single universe. So he reached, in public, in an official document, for other worlds. Think about how unusual that is. Engineers are not, as a rule, romantics. They are the people who tell you exactly how the trick works, who pull back the curtain and show you the gears. And here was a master engineer, effectively saying, the gears in this machine seem to extend somewhere I cannot point to, somewhere outside the world we can see. Whether he was right or wrong, there is something almost vulnerable in that admission. He was telling the truth about the edge of his own understanding, and his answer, stripped of all the headlines, is really just an answer to our central question. Where did the computation happen? Neven's answer, following Deutsch, is that it happened in the other branches, that the machine reached across the multiverse, and the work was shared among countless parallel versions of that chip, in countless parallel laboratories, each doing a piece, all of them interfering together to produce the single answer that appeared in our world. That is the claim. That is the whole astonishing claim in one sentence. But to know whether that claim is true, or even whether it is the kind of thing that can be true or false, you cannot just look at the chip. The chip will not tell you. The numbers it produces are perfectly real and perfectly agreed upon. What people disagree about is what those numbers mean, and that disagreement does not come from the machine at all. It comes from a wound at the very base of quantum physics, a question the founders of the theory could not answer in the 1920s, and that no one has been able to answer since. Every interpretation Neven's critics prefer, and the interpretation Neven himself prefers, are all just different attempts to bandage that same wound. So before we can referee the fight, we have to look directly at the thing they are fighting over. Let me show you the hole at the very center of physics. Is less than break time equals 1s is greater than number. Part 5. The question physics has dodged for a century. The hole has a name. Physicists call it the measurement problem, and despite the dry, technical sound of those two words, it is one of the most genuinely bewildering puzzles in all of science. It has never been solved. It has only been managed, worked around, and in many cases, politely ignored for the better part of 100 years. And everything we have talked about tonight, the parallel universes, the borrowed computations, the strange answer to where the work gets done, all of it flows directly out of this one unsolved problem. So let me lay it out for you as cleanly as I can. Quantum mechanics has, at its center, an equation. It is called the Schrödinger equation, and it is one of the most successful pieces of mathematics in the history of the human species. It describes how a quantum system changes over time, and it does so with perfect smoothness and perfect certainty. Given the state of a system now, the equation tells you exactly how its possibilities will flow and develop into the future. There is nothing random about it. It is as deterministic, as clockwork precise, as anything in old-fashioned physics. And what it describes, as it evolves, is that shimmering superposition we keep returning to, the combination of all possibilities, spreading and branching and interfering, smoothly and continuously, forever. But here is the problem, and it is a strange one. When you actually go into a laboratory and measure a quantum system, you never see a smooth combination of all possibilities. You see one thing: the particle is here, or it is there, but never some ghostly mixture of both. The needle on the instrument points to a single number. The detector clicks once, in one place. Reality, when you look at it, always shows you a single, definite outcome. And the probabilities of which outcome you get follow a beautiful rule. But the point is, you get one of them, just one, every single time. So now look at the contradiction directly. The equation says the system is a smooth, spreading combination of every possibility, evolving with perfect certainty. Your experience says you always see exactly one possibility, chosen apparently at random. These two things cannot both be the full story, because they describe different things. And the official way physics has handled this for a century is, frankly, a little embarrassing when you say it out loud. The standard recipe says, the system evolves smoothly, according to the equation, spreading into all its possibilities, right up until the moment someone measures it. And then, at that moment, the whole spread of possibilities suddenly and instantaneously collapses down to one. The many become the one, and you see that one, but nothing in the equation describes that collapse. It is not in the mathematics. It was added by hand, bolted onto the theory by its founders, because it had to be there to match what we actually observe. Nobody can tell you what counts as a measurement. Does it require a conscious observer? A laboratory instrument? A single stray atom bumping into the system? Where exactly is the line between the smooth quantum world that follows the equation and the sharp classical world of single outcomes that we live in? The theory does not say. It works flawlessly for prediction, and it stays completely silent on this most basic question of what is actually happening. That silence is the measurement problem. You may have heard of Schrödinger's cat, and almost everyone gets the point of it exactly backwards, so let me set it right, because it lands perfectly here. Erwin Schrödinger, one of the founders of the whole theory, imagined a cat in a sealed box, with its life tied to a single quantum event, so that according to the smooth equation, the cat ends up in a superposition of alive and dead, both at once, until someone opens the box and looks. Now, Schrödinger did not invent this to show how wonderfully spooky quantum mechanics is. He invented it as a complaint. He was pointing at the theory and saying, "Look how absurd this becomes when you take the collapse story seriously. Look how ridiculous it is to claim the cat is genuinely both alive and dead until observed." The cat was a protest. It was Schrödinger saying, surely the theory must be incomplete because this cannot be the literal truth. And here we are, 100 years later, and we still cannot agree on whether he was right to complain. Now, here is the single most important fact in this entire video, and I want you to hold it above everything else, because it is the key that unlocks the whole argument about the chip. Every interpretation of quantum mechanics, every competing story about what is really happening, predicts exactly the same experimental results. Every one of them. When you run the experiment, they all tell you the detector will click here with this probability and there with that probability, and they all agree down to the last decimal place, and they all match what we measure. There is not a single experiment anyone has yet devised that can tell them apart. They are not different theories in the usual scientific sense. They are different stories told over an identical set of true facts. Let me make sure that lands, because it changes the nature of the whole debate. When two scientific theories disagree, normally you go into the lab, you run an experiment, and reality tells you which one was right. That is how science settles things. But here, reality refuses to referee. You can run any experiment you like, and every interpretation predicts the same outcome, so the experiment never picks a winner. The disagreement is not about what will happen. It is about what is real behind what happens. It is about meaning, and questions of meaning, when no experiment can decide them, start to feel less like physics and more like philosophy, even though they sit at the absolute foundation of our most precise science. So let me show you the menu, the competing stories, without yet judging between them. One story says the collapse is real, an actual physical event. When you measure, the possibilities genuinely vanish and one becomes real. Do not ask how or why, just accept that measurement collapses the wave. This is the orthodox view, the one most textbooks teach. A second story is Everett's many worlds, the one Deutsch and Neven favor. It says, there is no collapse, ever. The smooth equation is the whole truth. All the possibilities stay real, and reality branches so that every outcome happens in its own world. A third story says particles always have definite positions, guided by a hidden wave. So there is only ever one world, and the appearance of spreading possibility is just our ignorance of where things really are. And a fourth says the quantum state was never a description of reality at all, but only a description of what an observer knows, a catalogue of information rather than a picture of the world. Do you see now what Neven actually did? When he said the computation happened in many parallel universes, he was not reporting a discovery. He was choosing the second story off that menu, the many worlds story, and applying it to his machine. And when his critics objected, they were not denying his data. They were preferring a different item from the same menu, the first story, or the third or the fourth, each of which explains the very same chip without any other universes at all. The fight over Willow is really the 100-year-old fight over the measurement problem, wearing the costume of a modern computer. This is why a small chip on a laboratory bench can reopen an argument between Einstein and Bohr from a century ago. It is the same argument. It never ended. It just went quiet for a while, because the practical physicists got tired of it and decided to shut up and calculate, as the saying went, to use the equation without worrying about what it meant. That phrase, shut up and calculate, is worth sitting with, because it captures an entire century of a peculiar bargain. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions have been confirmed to an accuracy of better than 1 part in a billion in some experiments, a level of agreement between theory and measurement that no other human idea has ever achieved. And yet, the people using this flawless tool, for the most part, quietly agreed not to ask what it was telling them about the world, because every time they asked, they fell into the measurement problem and could not climb back out. Imagine owning a map that guided you perfectly every single time to any destination you named, but that nobody could explain, a map whose lines corresponded to nothing anyone could point to in the territory. You would use it. Of course you would use it. It works. But some part of you would lie awake, wondering what exactly you were holding. That is the relationship physics has had with its own most successful theory for 100 years, and the chip in Santa Barbara walked into that uneasy peace and started asking the forbidden question out loud again. Einstein himself never made that bargain. He could not accept a theory that, in his view, left reality undefined until someone looked, and he spent the last decades of his life arguing that quantum mechanics, for all its success, had to be incomplete, that there must be some deeper layer of definite facts underneath. God does not play dice, he famously objected. And Bohr, his great opponent, replied that Einstein should stop telling God what to do. They argued this for years, two of the most powerful minds of their era, and they never reached agreement, and neither did the field after them. The argument simply never closed. It only became unfashionable to bring up. The machine in Santa Barbara dragged the question back out into the open because it made the stakes feel enormous. And I want to be very honest with you. This is genuinely unsettled, even among the most brilliant people alive. There is no consensus. Anyone who tells you the matter is obviously closed, in either direction, is selling you a comfort that the actual physics does not provide. So let us do the fair thing. Let us give the skeptics the floor, the people who heard Neven's claim and said, "No, you have made an error. You have mistaken a piece of mathematics for a place." Because their strongest argument is sharp, and it is honest, and any real understanding of this story has to pass through it, they are about to tell us that the other universes were never there at all. That what looks like a multiverse is just the shape of an equation. And to know whether they are right, we have to follow them into the strange abstract space where quantum mathematics actually lives. Is less than break time equals 1s? Is greater than number, part 6, the skeptic's universe. It's just Hilbert space. The sharpest version of the skeptical reply came from an astrophysicist and science writer named Ethan Siegel, and he did not mince words. He said that Hartmut Neven had conflated two things that are not the same. He had confused the notion of a quantum mechanical space called Hilbert space with the notion of parallel universes and a multiverse. And if that is true, if those really are two different things that got mistaken for one another, then the entire parallel universe claim collapses, not into another world, but into a simple error of interpretation. So we have to understand what Hilbert space is, and I will do my best to make this abstract idea something you can actually picture. When physicists describe a quantum system mathematically, they do not write the possibilities down on an ordinary map with 3 directions, length and width and height, the way you would describe the location of a chair in a room. Quantum states live in a different kind of mathematical arena, one with as many dimensions as the system requires, and for a quantum computer, that number of dimensions is enormous. This arena is called Hilbert space. It is the abstract stage on which the equations of quantum mechanics are performed. When we said earlier that 105 qubits track 4 followed by 31 zeros of combinations, what we were really describing was a Hilbert space with that many dimensions. The state of the machine is like a single arrow pointing in a direction within that unimaginably many-dimensioned space. Now here is the skeptic's point, and it is a good one. Those enormous numbers, the combinations, the 10 to the 500th resources in Deutsch's argument, all of them are dimensions of this abstract mathematical space. And the skeptic says, a dimension of a mathematical space is not a universe. It is a coordinate. It is a number in an equation. To say that each of those dimensions is a real, physical, parallel world, full of real parallel laboratories and real parallel copies of you, is not something the mathematics forces on you. It is an extra story you have chosen to tell on top of the mathematics. The equation needs the dimensions. It does not need them to be worlds. Let me give you an analogy that makes the skeptic's case feel reasonable, because it genuinely is reasonable. Think about how meteorologists predict the weather. A serious weather model might track 1 trillion different variables, the temperature and pressure and humidity and wind at 1 trillion points across the atmosphere, all evolving together in a gigantic system of equations. Mathematically, that model lives in a space with 1 trillion dimensions. But no one in their right mind stands up and says, therefore the storm is being computed across 1 trillion parallel skies, therefore there must be 1 trillion real atmospheres somewhere doing the work. We all understand instantly that the trillion dimensions are bookkeeping. They are how we keep track of a complicated single thing. They are not 1 trillion real places. The skeptic says the multiverse claim makes exactly this mistake, just dressed up in the glamour of quantum physics. The huge numbers are real as mathematics. Calling them real as worlds is a leap nobody has to take. And the skeptic has more than an analogy. They have living, breathing, alternative theories that explain everything the chip does without a single extra universe. Take pilot wave theory, sometimes called the de Broglie-Bohm interpretation. In this picture, particles always have perfectly definite positions at every moment, whether you look or not. There is no spreading into all possibilities. Not really. Instead, there is a real, physical wave that guides the particles along, pushing them this way and that. And our uncertainty about where the particle is comes only from our ignorance of its exact starting point, not from any genuine fuzziness in reality. Pilot wave theory reproduces every single prediction of standard quantum mechanics. Every experiment comes out the same, and it does it all in one world, with one definite history, no branching, no parallel copies. It is a complete counterexample to the claim that you must have many worlds. Then there is the orthodox Copenhagen view, the one most physicists were raised on, and the Copenhagen answer to our central question is wonderfully, maddeningly blunt. It says the question is meaningless. Where did the computation happen? Wrong question. The wave function is not a real object out in the world. It is a tool for calculating the probabilities of measurement outcomes. Asking where the computation physically lives is like asking what color the number 7 is. You are taking a calculating device and demanding it be a place. Stop asking, says Copenhagen. Run the equation, get your answer, and do not pretend the mathematics is a map of hidden worlds. It is a deflating answer, but it is internally consistent, and a great many working physicists are perfectly happy with it. Now I want to bring in a third voice, because this person is neither a hype man nor a denier, and his judgment is, I think, the most trustworthy in the whole debate. His name is Scott Aaronson, and he is one of the most respected theorists in quantum computing, a man who has spent his career thinking precisely about what these machines can and cannot do. When the Willow result and the multiverse comments swept across the internet, people asked him what he made of it, and his answer was beautifully measured. He said that the new experiment does not add anything new to this old debate. It is, in his words, yet another confirmation of the predictions of quantum mechanics. What those predictions mean for our understanding of reality, he said, can continue to be argued as it has been since the 1920s. In other words, nothing about the chip moves the needle on the philosophy. The chip confirms quantum mechanics works, which we already knew. It does not pick a winner among the interpretations, because nothing can. But here is the part that keeps the skeptics from getting a clean victory, and it is important that I give it to you, because the honest picture has no easy winner. That same Scott Aaronson, who is so careful not to overclaim, also freely admits that many worlds is the obvious story if you take the Schrödinger equation as applying to the entire universe, everywhere, always. He has said that once you accept that the equation is universal, the multiple worlds seem almost unavoidable. And he has said something even more damaging to the skeptics, which is that every concrete alternative to many worlds currently on the market is, in his words, contrived and unsatisfactory. So the orthodox view that calls the question meaningless, the pilot wave view with its hidden guiding wave, all of them have their own awkward problems and their own unexplained machinery. The skeptics can knock down the multiverse claim, but they cannot replace it with something obviously cleaner. Everyone is standing in a house with cracks in the walls, pointing at the cracks in everyone else's house. I think it helps to name exactly what each side is paying, the price each interpretation charges you for its comfort, because that is the real choice on the table. If you take the orthodox view that the question is meaningless, the price you pay is that you must accept a theory that works perfectly while refusing to say what it describes, and you must draw an arbitrary line between the quantum world and the classical one without ever explaining where that line is or why it is there. If you take the pilot wave view, with its particles always carrying definite positions, the price is that you must accept a hidden wave that reaches across any distance instantaneously, a kind of non-locality that Einstein himself found troubling, a universe wired together faster than light beneath the surface. And if you take the many worlds view, the one Neven reached for, the price is the most extravagant of all. You must accept that every quantum event spawns realities without number, that there are uncountable copies of you and of everything branching endlessly, an ocean of parallel existence that you can never see, never visit, never confirm. There is no free option. Every account of reality that survives contact with the experiments asks you to swallow something that violates your common sense. The only real choice is which impossible thing you find easiest to live with. So where does that leave us with our central question, the one that has run through every part of this story? Where did Willow's computation happen? And the honest, uncomfortable answer is that the machine cannot tell us and may never be able to tell us. Because all of these pictures, the real branches, the abstract mathematics with no extra worlds, the guiding wave, the catalogue of information, all of them predict that Willow works exactly as it does. The chip is a kind of mirror. The multiverse believer looks at it and sees other universes shimmering behind the result. The orthodox skeptic looks at it and sees clever metal and an abstract equation. And both of them are looking at the identical machine, producing the identical numbers, and neither can prove the other wrong with any experiment we currently know how to perform. That could be the end of the story, and if it were, it would still be a strange and beautiful one. But it is not the end, because in the months and years after Willow, The world did not simply argue. Two very different experiments pushed harder on this refusal of reality to give up its secrets. In one of them, Google built something that was no longer a useless benchmark, something that could run a piece of a quantum system backward, like reversing time on the flow of information itself, and pull out answers no ordinary machine could reach. And in another laboratory entirely, physicists caught two observers in the act of disagreeing about what had actually physically happened, an experiment that suggested reality itself might not hand the same facts to everyone. So let me take you to the next strange thing the machines found, the one where they learned to listen for a reply from a system running in reverse. Is less than break time equals 1s is greater than number. Part 7. Quantum echoes and running reality backward. The skeptics had a genuinely strong card to play against the Willow result, and I gave it to you a moment ago, but let me sharpen it now because it is exactly what the next chapter answers. The skeptics could say, fine, your chip is fast, but the thing it was fast at, that random circuit sampling, is a party trick. It solves no real problem. You designed a task specifically to be hard for ordinary computers and easy for yours, and then you acted amazed when your machine won the game you built. Until a quantum computer does something actually useful, something we care about, faster than a classical computer can, all of this multiverse talk is just noise around a benchmark. That was the cleanest, most deflating criticism available, and it was fair. In October of 2025, Google answered it. On the 22nd of that month, the same team, using the same Willow chip, announced something they called quantum echoes, and it carried a phrase that had never honestly been attached to a quantum computer before. They called it the first demonstration of a verifiable quantum advantage. Each of those words was chosen with care, and to understand why this mattered so much more than the first announcement, you have to understand both halves, the verifiable and the advantage. But first, let me tell you what the machine actually did, because the method itself is one of the eeriest things I have come across in physics, and it speaks directly to our question about where reality keeps its secrets. The technique works like this. You take the quantum system, the array of qubits on the chip, and you send a carefully shaped signal into it, setting it evolving forward, letting the information spread and tangle through the system, the way ripples spread across a pond after a stone drops in. Then you do something almost mischievous. You reach in and you nudge a single qubit, just one, a tiny, deliberate disturbance. And then you run the entire system backward. You reverse its evolution, step by step, unwinding the spreading and the tangling, trying to make the ripples flow back to where they came from. And you listen for what returns. In a system with no disturbance, running it forward and then perfectly backward would bring you exactly back to the start, the ripples gathering themselves up and the pond going still. But because you nudged that one qubit in the middle, the reversal does not come back clean. Something returns changed, and by measuring precisely how it returns, how the reversed signal interferes with itself, you learn something extraordinarily detailed about how information moved through the system. Let me give you the image fully, because it deserves to be felt slowly. Imagine standing at the edge of a perfectly still pond at night. You drop a single stone, and you watch the rings spread outward into the dark, growing wider and fainter, the energy of that small splash dispersing across the whole surface until the pond looks calm again, as though nothing had happened. Now, imagine you possessed a godlike power to reverse every molecule of water, to send every ripple flowing precisely backward, gathering the dispersed energy from across the entire pond, focusing it until the rings rush inward and the water leaps up and the stone jumps back into your waiting hand. That impossible act of undispersing, of gathering scattered information back into a single point, is, in spirit, what this machine does. Except it does not do it with water. It does it with quantum information. And the small change you made in the middle, the nudge to 1 qubit, shows up in exactly how the reversal fails to be perfect. And that failure is the measurement, the precious signal you were after. The proper name for the physics here is an out-of-time order correlator, which is a mouthful, so let us just hold the plain meaning. It is a tool for measuring how information spreads, tangles, and scrambles through a quantum system by sending it forward, perturbing it, and running it back. And the numbers Google reported for how fast Willow could do this were, once again, staggering, but in a more meaningful way than before. The quantum echoes algorithm ran about 13,000 times faster on Willow than the best-known classical algorithm running on one of the world's fastest supercomputers. To get a single one of these datasets, involving 65 qubits and very long, complicated sequences of operations, the supercomputer would need an estimated 3.2 years for each data point. Willow produced a whole series of them in a matter of minutes. 3 years of work by the most powerful classical machine on Earth, against a few minutes of work by a chip the size of a coin. But the speed is not the part that broke the skeptic's best objection. The word that did that was verifiable. Let me explain why that single word is the most important one in the entire announcement, maybe in this entire story. Remember the skeptic's history lesson, which we will look at more closely soon, that earlier quantum supremacy claims had a way of crumbling. One of the reasons they crumbled is that the random circuit sampling results were, in a fundamental sense, unverifiable. The machine produced an answer that was, by design, so hard to compute that no classical computer could check whether it was even correct. You had to take the quantum computer's word for it. And a result that nobody can independently confirm sits on shaky ground, because if you cannot check it, you cannot be fully sure the machine did what it claimed, rather than simply producing convincing-looking noise. Quantum echoes was different in a way that matters enormously. The result it produces can be confirmed. In particular, 2 separate quantum processors running the same algorithm independently get the same answer. That repeatability, that agreement between independent machines, is one of the oldest and most powerful tools in all of science, the foundation of how we trust any result. If you do the experiment over here, and I do it over there, and we both get the same number, that number starts to look like a real feature of the world rather than a quirk of one apparatus. For the first time, a quantum computer had produced an advantage that other quantum computers could vouch for. The result could be pinned down, checked, trusted. And then there was the third thing, the one that finally answered the deflating criticism head-on. They used it for something real. In a proof-of-principle experiment, done together with researchers at the University of California, Berkeley, the team turned the quantum echoes technique into a kind of measuring instrument, a quantum ruler for the structure of molecules. They studied 2 molecules, one made of 15 atoms and a larger one made of 28 atoms. Now, there is already a well-established technology for probing molecular structure called nuclear magnetic resonance, the same basic physics behind the magnetic resonance imaging machines in hospitals. And the quantum computer's results matched what nuclear magnetic resonance produced, which confirmed the method was sound. But the quantum approach also revealed information about the molecule that the traditional method could not easily extract. The benchmark had grown up. It had become a tool that could tell you something true about a real physical object that you wanted to understand. So step back and feel where we have arrived. We started with a machine that did something useless, impossibly fast, and prompted its builder to invoke other universes. The skeptics said, useless is the key word. Come back when it does something real. And the machine came back, and now it could run a quantum system backward in time, in effect, gathering scattered information into a returning signal, verified by a second independent machine, and use that ability to read the hidden structure of a molecule more completely than our best existing instruments. This is no longer a party trick. This is an instrument that does something the universe does not seem to allow ordinary matter to do, faster than every atom in our world could simulate it. I want to slow down on that time reversal idea, because it is easy to nod past it and miss how profound it is. In the world you and I live in, time runs one way. A cup falls and shatters, and it never reassembles. Cream stirred into coffee never unstirs itself. A drop of perfume disperses through a room and never gathers itself back into the bottle. This one-way flow, this relentless spreading out, is one of the most basic features of our experience. So basic that we rarely even notice it as a fact that needs explaining. It is tied to a quantity physicists call entropy, the steady increase of disorder, and it is, as far as we know, the very arrow that points the way we call forward in time. And what this machine does, in its own confined quantum way, is run a piece of that arrow backward. It takes information that has spread and scrambled, the way perfume disperses, and it gathers it back, focuses it, reads the original shape out of the returning signal. It does not violate the laws of physics to do this, because it does it under exquisite control, in perfect isolation, in a way the messy, macroscopic world never permits. But it is, in spirit, the thing we are told can never happen. It is the cup reassembling, and the fact that it works, reliably, verifiably, on a chip you could hold in your palm, is one more place where the surface rules of our experience turn out to be only the surface. So the machine does the impossible thing twice over. It computes faster than the universe can keep up, and it runs information backward against the current of time, and it uses both of those powers to tell us something true about a real molecule. Whatever you decide to believe about other worlds, you cannot dismiss this as a stunt anymore. It is a working instrument operating in a regime our intuitions were simply not built to handle. And do you see how this sharpens our central question rather than softening it? With the useless benchmark, a skeptic could shrug and say, who cares where a meaningless calculation happened? But now the machine is reaching into the actual structure of a molecule, running information backward, pulling out real answers 13,000 times faster than the combined might of our fastest classical computer. David Deutsch's old question presses harder than ever. If the resources required to do this are not present in the small cold chip, and the work is genuinely being done, and the answers are genuinely real and verifiable and useful, then where is the work happening? The question is no longer abstract. It is no longer a thought experiment about factoring impossibly large numbers. It is sitting on a laboratory bench in Santa Barbara, measuring molecules, demanding an answer. I want to be honest, as I have tried to be at every step, about what this does and does not prove. Quantum echoes does not prove the multiverse. Let me say that plainly, because it would be so easy to let the momentum of the story carry you past it. What quantum echoes proves is that the hardware is genuinely doing something extraordinary, that the advantage is real and checkable rather than a mirage, and that quantum computers are crossing from spectacle into usefulness. It is a monumental result for the field, but it is still, like everything else, perfectly consistent with every interpretation of quantum mechanics on our menu. The many worlds believer sees the work being shared across branches. The skeptic sees an exquisitely engineered exploration of an abstract mathematical space. The machine refuses, once again, to take sides. What it has done is raise the stakes by making the impossible thing useful and therefore impossible to dismiss. So let yourself sit here for a moment in the cozy quiet of this thought, because this is where the story stops being a quarrel about a press release and becomes something you can almost hold in your hands. There is a real object in a real room that takes information, scrambles it the way a chaotic universe scrambles everything, then unwinds that scrambling and reads the result faster than the cosmos itself could keep up. Whatever you believe about other worlds, that object exists and it works. And the technique it uses to work, this business of scrambling information and then chasing it backward, did not come from computer science at all. It came from the study of the most extreme objects in the universe, the places where information seems to vanish entirely. To understand what the machine is really probing, we have to take a brief detour to the edge of a black hole, because that is where this strange method was born, and it tells us something about where reality hides the things it takes from us. Is less than break time equals 1s is greater than number. Part 8. Scrambling, black holes, and where information hides. The mathematics behind quantum echoes was not invented to build a faster computer. It was invented to understand the most violent and mysterious objects we know of, black holes, and the puzzle of what happens to information when it falls into one. So let me connect those two worlds quickly, because the link is genuinely beautiful and it feeds directly back into our central question. When information falls into a chaotic quantum system, something strange happens to it. It does not get destroyed, at least not according to the fundamental equations, but it gets spread out, tangled up, mixed into the system so thoroughly that it becomes impossible to recover by any ordinary means. Physicists call this scrambling. Picture dropping a single drop of ink into a turbulent, churning tank of water. The ink is still there, every molecule of it, but within moments it has been stirred so completely through the whole tank that you could never gather it back, never reconstruct the original drop. The information about where the ink started is technically still present, hidden in the precise arrangement of countless molecules, but for all practical purposes it has been lost to the chaos. That is scrambling, and quantum systems do it ferociously fast. Black holes appear to be the fastest scramblers in the entire universe, and that fact sits at the center of one of physics' deepest unsolved fights. The physicist Stephen Hawking argued that black holes actually destroy information, that whatever falls in is gone forever, erased from reality. But the fundamental laws of quantum mechanics insist that information can never truly be destroyed, only rearranged. Those two claims cannot both be true, and the contradiction between them, the black hole information paradox, has occupied the most brilliant minds in physics for half a century without a clean resolution. To even study the problem, physicists needed a mathematical tool that could measure how fast information scrambles, how quickly it spreads beyond recovery. And the tool they developed is the very same out-of-time order correlator that Willow ran. So pause on what that means. A small chip in a California laboratory is now running the exact mathematics that physicists use to probe the edges of black holes, the bookkeeping of where information goes when reality appears to swallow it whole. The machine takes information, lets it scramble the way a black hole would scramble it, and then, astonishingly, partly unwinds that scrambling, chasing the lost order backward and reading what returns. It is doing, in miniature and under control, a version of the thing we cannot do to a black hole, which is to reverse the disappearance and recover what was hidden. And here is the connection back to everything we have been circling, because it is the same shape of mystery from two directions. When we ask where the computation happened, we are asking where reality keeps the work it will not show us directly. When physicists ask where the information goes inside a black hole, they are asking where reality keeps the things it appears to take from us. Both questions point at the same suspicion, that beneath the surface world of single outcomes and visible objects, there is a hidden layer where the real bookkeeping is done, a place that does the work and keeps the receipts out of sight. The machine on the bench and the black hole in the sky may be asking us the same question. So let us follow that suspicion to an experiment that did not use a computer or a black hole at all, but instead caught two observers in the act of disagreeing about what was real. Is less than break time equals 1c, is greater than number, part 9, Wigner's friend, and when two people cannot agree on what happened. Everything we have explored so far comes back to one disturbing possibility: the idea that reality beneath the level of measurement is not a single, solid, shared thing. The multiverse interpretation is one way of taming that possibility, of saying, all the outcomes are real, just in separate branches, so nothing is lost and the strangeness has a home. But to feel why physicists reach for such an extravagant idea in the first place, you have to confront the strangeness directly, and in 2019, a group of experimenters managed to drag that strangeness out of the realm of thought experiments and into an actual laboratory. To understand what they did, we need to meet a puzzle that the physicist Eugene Wigner dreamed up decades ago, a puzzle that has quietly tormented the foundations of the field ever since. Eugene Wigner asked us to imagine a friend. This friend is a scientist, sealed inside a perfectly isolated laboratory, and inside that lab the friend performs a quantum measurement, looking at a particle that is in a superposition of two states. From the friend's point of view, inside the sealed lab, the measurement is perfectly ordinary. The friend looks, the superposition resolves, and the friend sees one definite result. Let us say the particle was measured as up. To the friend, that is simply what happened. The fact is settled. The particle is up. But now consider Wigner himself, standing outside the sealed laboratory with no information about what happened inside. According to the smooth Schrödinger equation, the one that never collapses on its own, Wigner must describe the entire contents of that lab, the particle and the measuring device, and the friend and the friend's brain and the friend's memory of the result, all of it together, as one enormous quantum system that is still evolving smoothly. And that means, from Wigner's point of view on the outside, the whole lab is in a superposition. Not just the particle, but the friend too. From outside, the friend is in a combination of having seen up and having seen down, both at once, because nothing from Wigner's perspective has forced a collapse. Now look at the contradiction, and let it really sink in, because it is not a trick of language, it is a genuine clash. The friend, on the inside, is certain that a single, definite thing happened. The particle was up. One fact, settled, real. Wigner, on the outside, using the same physics, must describe the friend as being in a superposition of two contradictory outcomes, neither one settled. So, which is true? Did one definite thing happen inside that lab, or not? Is there a fact of the matter about what the friend saw, a fact that exists independently of who is asking? Wigner's thought experiment suggests that quantum mechanics, taken seriously, may not give a single observer-independent answer to that question. The friend has their reality, Wigner has his, and the theory does not obviously force them to be the same. For a long time, this remained a thought experiment, a paradox to argue about over coffee, because you obviously cannot put a conscious human friend into a perfect quantum superposition inside a sealed lab. But in 2019, a team of physicists, led by Massimiliano Proietti, found a clever way to capture the essence of the paradox in a real experiment. They could not use human friends, of course. Instead, they used photons, particles of light, as stand-ins for the observers. They built an arrangement with 6 entangled photons, a setup elaborate enough that some of the photons played the role of the friends, making measurements inside their sealed labs, while others played the role of the outside observers, the whiners, describing those labs from outside. The result was published in the journal Science Advances, and what they found was genuinely unsettling. To test whether the inside view and the outside view could be reconciled into a single shared reality, the experimenters set up something called a Bell-type inequality, a kind of mathematical referee. The idea behind such inequalities is one of the most powerful tools in all of physics. You construct a statement that must be true if certain reasonable assumptions about reality hold, assumptions like the idea that facts are objective and shared, that the inside observer and the outside observer are describing the same single world. If the experiment obeys the inequality, the reasonable assumptions survive. If the experiment violates it, then at least one of those comfortable assumptions about reality has to be abandoned. And the experiment violated the inequality by 5 standard deviations, which in the language of physics means the result is about as solid as these things get, very far from any fluke. So let me tell you what that violation means, carefully, because this is exactly the kind of result that gets wildly exaggerated, and I promised you honesty rather than spectacle. The careful statement is this: if you want to hold on to a few very reasonable assumptions, namely that the observers have freedom in choosing what to measure, and that influences do not travel faster than light between distant places, then the experiment is telling you that the inside observer and the outside observer cannot both assign a single, shared, objective fact to what happened in the measurement. Their accounts of reality cannot be merged into one consistent story that they both agree on. In the language some physicists used afterward, observers may be entitled to their own facts. Now, the headlines, predictably, took this and ran straight off a cliff. They announced that science had proven there is no such thing as objective reality, that nothing is real, that the universe is whatever you want it to be. That is not what the experiment showed, and I do not want to feed you that overstated version, because it is a disservice to something that is astonishing enough when stated accurately. The accurate version is more disciplined, and I think more interesting. It is that, under a specific and reasonable set of assumptions, the facts about a measurement outcome may be observer-dependent rather than universal. Not that reality is a free-for-all, but that the simple, common-sense picture where there is one set of facts that everyone shares regardless of their perspective runs into serious trouble at the quantum level. The trouble is real. The free-for-all is not. It is worth being precise about the escape routes, because the experiment does not leave you with only one disturbing conclusion. It leaves you with a choice among several, and every one of them costs you something you would rather keep. The result says that you cannot simultaneously hold on to all of these comfortable assumptions at once. You would like to believe that measurements have single objective outcomes that everyone would agree on. You would like to believe that observers are free to choose what they measure. You would like to believe that no influence travels faster than light. And you would like to believe that the quantum description applies to everything, including observers themselves. The experiment says you must give up at least one of those. Maybe outcomes are not objective and shared. Maybe there is some hidden faster-than-light wiring. Maybe observers are not as free as they feel. Each option wounds something we take for granted, and the universe, through this 6-photon arrangement, is calmly informing us that we do not get to keep them all. And whichever one you surrender, notice that you have been pushed into the same neighborhood we kept arriving at with the computer. Give up objective shared facts, and you are halfway to either many worlds or the observer relative view. Accept hidden faster-than-light wiring, and you are in pilot wave territory. The two stories, the machine that outcomputes the universe and the observers who cannot share a fact, are not just both strange. They are strange in the same direction, herding us toward the same small set of unsettling pictures of what reality must be underneath. And do you feel how directly this connects back to our machine, to Willow, to the central question that has run through all of this? The multiverse interpretation, the one Neven invoked, is in large part an attempt to rescue us from exactly this discomfort. Think about it. In Wigner's puzzle, the central problem is that the friend saw one outcome while Wigner has to describe both. But in the many worlds picture, there is no paradox at all, because the friend genuinely saw both outcomes in two separate branches. In one branch, the friend saw up, and in another branch, equally real, the friend saw down, and Wigner's superposition description is simply the honest acknowledgement that both branches exist. the disagreement dissolves. The many worlds interpretation takes the observer dependence that the experiment revealed and explains it away by saying, of course, observers seem to have different facts, because there are different versions of the observers, each living in a different branch of a reality that has room for all of them. So this is one way the strangeness gets tamed, by multiplying worlds until every observer's fact has a place to be true. But I want to be fair, because it is not the only way, and the honest map of this territory has more than one road. There is another family of interpretations, going by names like the relational view and a position called Cubism, which take a completely different escape route. They say there is no need for extra worlds at all. Instead, they say the quantum state was never a description of objective reality in the first place. It is a description of a particular observer's information, an observer's relationship to the system, all the way down. From that point of view, of course, the friend and Wigner have different states for the lab, because they have different information, different relationships to it, and there simply is no observer-independent fact waiting underneath for them to agree on. The observer dependence is not a paradox to be explained away with many worlds. It is the fundamental nature of things, baked in from the start. I find it remarkable that the same experimental result can be absorbed in two such opposite ways, by adding countless worlds, or by denying that there was ever one objective world to begin with. And that is the lesson that keeps repeating in this story, like a pattern showing through everything we examine. The data is solid, the facts are agreed upon. It is the meaning that splits again and again into branches of its own. Two independent lines of evidence now sit in front of us. A computer that outcomputes the entire universe and prompts its maker to invoke other worlds, and an experiment in which observers cannot share a single fact about what happened. Both of them, from completely different directions, are pointing at the same hidden seam beneath the surface of the reality we experience. And notice, as we sit here in the quiet, how the further down we go, the less the universe behaves like the solid, single, dependable place it pretends to be when you are wide awake and looking at the ordinary world. The table is solid, the blanket is warm, the light in the room is exactly where you expect it. But underneath all of that steadiness, the most careful experiments we can devise keep whispering that the foundation is not single, not shared, not the simple objective stage we instinctively believe in. Perhaps the reason all of this feels almost forbidden, the reason the title of this video speaks of something we were never meant to see, is that our senses and our language and our deepest intuitions were all built for one branch, one observer, one world. We are creatures of the surface. We were shaped to track a single outcome, a single self, a single reality. And the mathematics, patiently, relentlessly, keeps describing something larger than the thing we were built to perceive. So we have two strange clues, the computer and the divided observers, and both of them suggest a hidden layer. But before we let ourselves be swept all the way into the multiverse, intellectual honesty demands that we slow down and ask a harder, more skeptical question. How many times before has science declared something impossible for ordinary machines, only to quietly walk the claim back a few years later? Because the history of these grand quantum announcements is not a clean march of triumphs. It is littered with miracles that shrank, and if we are going to take the machine's strangeness seriously, we have to first look honestly at how often the strangeness has turned out to be smaller than it seemed. Is less than break time equals 1s is greater than. Number, Part 10. The History of Shrinking Miracles. Before we decide that a machine has brushed up against another universe, we owe it to ourselves to remember how often the word impossible has quietly turned into the word possible in this exact field. The story of quantum computing is not a smooth ascent of undeniable wonders. It includes at least one very famous claim that began as a miracle and then steadily shrank, and that story is worth telling because it is the reason the word verifiable, mattered so much in the second Willow announcement. Go back to 2019. Google, using an earlier chip called Sycamore, announced what they described as quantum supremacy, the first time a quantum computer had supposedly done something no classical computer could practically match. They reported that their machine had completed a task in about 200 seconds, a little over 3 minutes, that would take the world's fastest supercomputer around 10,000 years. It made headlines everywhere. It sounded like a clean, decisive crossing of a historic line the moment quantum machines pulled definitively ahead. But the 10,000-year claim did not survive contact with the rest of the scientific community. Almost immediately, IBM, a direct competitor with its own serious quantum program, pushed back hard. They argued that with a smarter use of the supercomputer's enormous storage, the same task could be done classically in a matter of days, not 10,000 years, and that was only the beginning. Over the following years, researchers kept finding cleverer classical algorithms and better ways to use ordinary hardware, and the supposed gap kept narrowing, the 10,000-year mountain eroding down towards something far more modest. The miracle did not vanish entirely, but it shrank, and it shrank in public, which was humbling. So here is the honest lesson, and I think it makes you wiser rather than more cynical. Estimates of how long a task would take a classical computer are not facts carved in stone. They are educated guesses about the best possible classical method, and human cleverness has a way of finding better methods than we expected. The gap between no classical computer could ever, and a classical computer managed it next year, has closed before, more than once. A careful person holds the 10 septillion year figure with that history in mind, not dismissing it, but not treating it as a sacred, unbreakable wall either. And this is precisely why the second result, quantum echoes, was built to be verifiable, why that word was chosen so deliberately. It was a direct answer to this history. A result that 2 independent quantum machines can confirm, a result that can be checked against a known method like nuclear magnetic resonance, is far harder to erode away than a lonely, uncheckable benchmark. The field learned from its shrinking miracle and built the next claim on firmer ground. But notice something crucial as we return to our thread. Even if a classical computer someday matches the raw speed, even if the numbers shrink again, that would not touch our real question at all. Our question was never about the size of the speed-up. It was about where a genuine quantum computation physically takes place, about the nature of the process itself. A faster classical rival would change the bragging rights. It would not change the mystery of where the quantum work gets done. And that mystery has one more layer to peel back, because if the other worlds are real, we are left with the most obvious and childlike objection of all, and we have not yet answered it. Is less than break time equals 1s is greater than number, part 11, why we only ever see one world. If the many worlds picture is true, if reality really is branching constantly into countless parallel versions, then a very simple question demands an answer, the kind of question a child would ask without hesitation. Where are they? If there are other versions of you, other branches, other outcomes all equally real, why can you not see them, hear them, feel them, bump into them? Why does the world around you look so stubbornly, completely single? Any honest account of the multiverse has to explain why it stays so perfectly hidden, and the answer is one of the most elegant ideas in modern physics. It is called decoherence. Here is the idea, told gently. A quantum system can only hold its delicate superposition, that shimmering combination of possibilities, as long as it stays isolated from its surroundings. The moment it interacts with the wider environment, with the countless air molecules and photons and stray particles constantly jostling everything, the information about its quantum state leaks out into all of that surrounding chaos. And once that information has spread into the environment, the different branches of the superposition lose the ability to influence one another. They can no longer interfere, no longer add, and cancel like ripples on a pond, because the environment has, in effect, recorded which branch is which. The branches stop talking to each other. This rapid, relentless leaking is decoherence, and it happens almost unimaginably fast for anything larger than a few particles. And here is the subtle, beautiful part. Decoherence does not necessarily destroy the other branches. In the many worlds picture, it simply makes them inaccessible. They are still there, still real, still playing out their own outcomes, but they have become permanently sealed off from ours, unable to interfere, unable to leave any trace we could detect. It is not that the other worlds are far away in space. It is that they have lost the ability to interact with us at all. They are, in the most complete possible sense, invisible, not hidden behind a wall we might one day climb, but separated by the very mechanism that gives us a stable, classical world to live in. There is an extension of this idea, developed by the physicist Wojciech Zurek, sometimes called quantum Darwinism, and it explains why we all agree on the world we do see. The environment does not just record which branch is which. It makes many redundant copies of certain stable pieces of information about a system, broadcasting them widely, so that many different observers, picking up many different fragments of that environment, all read the same story. The world looks solid and shared, in this view, because its most stable features get mass-produced across the environment, copied over and over until everyone who looks finds the same answer. Reality looks seamless precisely because the seams, the other branches, have been sealed away and the surviving story has been printed in countless copies. So tie this back to the title that brought you here, to that phrase about something we were never meant to see. If the many worlds picture is right, the other branches are invisible not by some accident or oversight, but by the very process that allows a stable, single, classical world to exist at all. Reality hides the seam in order to look seamless. We are built never to perceive the branching, because perceiving it would mean living in a world that never settled into the solid outcomes we depend on. And notice, this is also exactly why a quantum computer is so monstrously hard to build. The entire engineering challenge is to protect that fragile interference, those talking branches, from decoherence, to keep the environment from prying and sealing them off, long enough for the calculation to finish. Willow's great quiet achievement, the error correction we talked about, is in a sense a battle against the very mechanism that keeps the other worlds hidden from the rest of us. So when the machine reaches into whatever it reaches into, it is, if Deutsch is right, briefly holding open a door that reality works tirelessly to keep shut. And that reframes everything about where this story leaves us, which brings me to the only honest place to end, back at the question we started with, the one the machine cannot answer and cannot let us forget. Is less than break time equals 1s, is greater than number, part 12, where the computation happened. So here we are, after everything, back at the question that has run like a single thread through this entire night. When Willow did in 5 minutes what the universe does not contain enough time to do, where, physically, did the computation happen? We have walked all the way around this question, examined it from every side, and now I have to do the hardest thing a storyteller can do, which is to refuse to lie to you with a tidy ending. Because the truth is that the machine cannot tell us, and may never be able to. Let me lay the honest possibilities side by side, the way they actually sit in physics, with none of them crossed out. The first possibility is that David Deutsch and Hartmut Neven are right, that the computation happened across real, physical, parallel branches of reality, that the machine genuinely recruited the work of countless other versions of itself in countless other worlds, and that the impossible-seeming resources were real because they were drawn from a multiverse we cannot see. The second possibility is that Ethan Siegel and the orthodox physicists are right, that the computation happened in an abstract mathematical space, that the huge numbers are dimensions of an equation and not worlds at all, and that the whole multiverse story is a poetic mistake, the confusion of a map for a territory. And the third possibility is that the question itself is malformed, that there is no single objective fact about where the computation happened, because reality at its base is observer-relative information rather than a stage on which things occur. And here is the part I need you to really absorb, the part that is so easy to want to escape. Every single one of those possibilities is defended, right now, by brilliant, serious, careful scientists. Not one of them can be ruled out by any experiment we currently know how to perform. The chip cannot break the tie, because all three predict that the chip works exactly as it does. We are not waiting on a cleverer measurement that will settle it next year. We are standing at a genuine fork in our understanding of reality, and the machine, for all its impossible speed, points down all the paths at once and tells us nothing about which is true. So what did Willow actually do if it did not answer the question? I think it did something stranger, and in the end, more profound than answering ever could have been. It took a question that for 100 years lived only in philosophy seminars and thought experiments, a question that practical physicists had agreed to set aside so they could get on with their calculations, and it built that question a body. It gave the measurement problem a machine. It made the stakes of an old, abstract, almost forgotten argument suddenly impossible to ignore, by producing numbers so far beyond the universe's capacity that you cannot wave them away. The chip did not find another universe. The chip found the sharp edge of our own ignorance and pressed our fingers against it. And there is something worth noticing about why this particular question is so resistant, why it does not behave like other scientific puzzles that eventually fall to a clever experiment. Most mysteries in science are mysteries of fact. We do not know something, and then we build an instrument, and the instrument tells us, and the mystery closes. What is the universe made of? How old is it? What is at the center of our galaxy? Those are questions reality will answer if you ask it correctly. But the question of where the computation happened is not quite a question of fact. It is a question about which of several perfectly accurate descriptions corresponds to what is really there, when all of those descriptions predict exactly the same facts. And that is a kind of question we may not have the right tools to answer at all, not because our instruments are too crude, but because reality may simply not contain a detectable difference between the answers. The other universes, if they are there, are defined by their inability to be detected. The abstract mathematical space, if that is all it is, has no separate physical existence to find. We may be asking the world a question it has no mechanism to answer, like asking what is north of the North Pole. That is a strange and slightly vertiginous place for a science to find itself, and yet it is exactly where the most precise theory we have ever built has led us. We followed the mathematics step by careful step, each one confirmed by experiment, and it carried us to a doorway and then refused to tell us what lies on the other side, or even whether there is an other side at all. The machine on the bench is the sharpest version of that doorway anyone has ever constructed. It works. It does the impossible thing, and it stands there, humming quietly in the cold, as mute about its own deepest nature as the universe that built the physicists who built it. Think about David Deutsch in his house, the near recluse who spent 40 years insisting that the mathematics demanded other worlds. That quantum computation placed an intolerable strain on every interpretation, but the one almost no one wanted to believe. He built that conviction out of pure reasoning, decades before any machine could test the feeling of it. And he lived to see a device produce exactly the kind of number he had predicted would one day force everyone to look. He may be wrong. Many brilliant people think he is. But there is something moving about a person who follows an argument to its strange conclusion and then waits, patiently, for 40 years, for the rest of the world to feel the weight he felt all along. And think about Hartmut Neven, the engineer who looked at his own creation and could not contain it within a single world, who reached in public for the multiverse to explain the thing his own hands had built. Whether he was right or merely romantic, whether he overreached or saw clearly, there is an honesty in it that I keep returning to. He was telling the truth about the edge of his own understanding. He had made a machine that outran his ability to explain it within the boundaries of one universe, and rather than pretend otherwise, he said so, out loud, and let the world argue. Bring all the strands together now, in the quiet. The returning signal that runs backward through a system, gathering scattered information the way nothing in our ordinary world is allowed to. The two observers, who could not share a single fact about what happened in a sealed room, the computational resources that outstrip every atom in everything we can see, all of it, from every direction, circling the same patient suspicion that the reality you and I walk around in, the solid single world of one thing after another, is a thin and stable surface stretched over something far larger and far stranger, something the universe seems built to keep just out of our sight. We evolved to track one world, one outcome, one self. The machine is the first tool we have ever made that pushes its fingers past that limit and comes back holding numbers our intuition was never equipped to carry. And I want to leave you, before you drift off, with something gentle rather than frightening, because none of this should frighten you. If anything, it should make the ordinary world feel quietly miraculous. The fact that you can sit here, in one warm room, in one settled moment, with one continuous sense of being yourself, may be a kind of small triumph that reality performs constantly and invisibly on your behalf, sealing away the branching, printing the seamless world in countless copies, so that you never have to feel the ocean of possibility churning underneath. Beneath the solid table and the warm blanket and the single quiet outcome of this exact moment, there may be an unimaginable expanse of branching reality, doing arithmetic, holding every road not taken, every outcome that did not become yours. So perhaps the most unsettling thing these machines found is not another universe at all. Perhaps it is the discovery that we have now built something whose workings we cannot fully explain without arguing about how many universes there are, and that the universe, so far, seems perfectly content to let us keep wondering, to keep its deepest answer just beyond the reach of every experiment we know how to ask. We made a machine to compute, and it handed us back, instead, the oldest question there is, made new and made undeniable, glowing quietly on a bench in a cold room, waiting for us to be ready to understand it. And maybe, for tonight, it is enough simply to have looked,